Okay, so we are talking about computational complexity. So in the last class we have discussed three complexity class P, XP and R. So P is the set of all problems which can be solvable by polynomial time, and XP is the set of all problems which can be solvable by exponential type. So P is a subset of XP, and R is the set of all problem which can be solved in finite time. I mean, and after R all the problems is basically uncomputable problem. So, here all the problems are uncomputable. Okay. So, this is basically we have seen most of the decision problems are basically uncomputable problem. Decision problem means whether answer is yes or no. I mean whether we can given a chessboard, given a configure of the chessboard, whether white win or not. So, this is a decision problem. Given a graph, directed graph, whether there is a negative cycle. So, this is a decision problem, answer is yes or no, but this is in P, that detection of negative cycle. Now, there are problem like Tetris problem is basically this is also a decision problem. So, given a board and given a sequence of the blocks sequence, now the question is whether we can survive or not. So, this sequence are falling sequentially. So, whether we can survive or not, whether we can move this or this. So, now, so these are the complexity class we have discussed. Now, we talk about another class which is called NP. NP, it is not NP is not non-polynomial, it is non-deterministic polynomial NP. So, what is NP? This is basically set of all decision problem which are solvable in polynomial time, via a lucky algorithm. Okay. So, what do you mean by lucky algorithm? So, lucky algorithm means, so we can see there are many possibilities from a starting point. So, say this is a decision problem. So, we have there are many possibilities over here. So, from here we can go like this. So, in the dynamic programming problem we explore all the way. Now, so from here say we are going like here, these are the possible move. Okay. Now, suppose this is a decision problem in some, so this is a no, this is no, and if we have a yes in some, if we have a no everywhere, then whatever move we take, whatever path we choose, the decision will be no. But if there is a yes, then every time we choose a path, and that is magic. I mean, we choose a path and that is called lucky path, that will lead us to yes. So, we will not explore all the paths like in dynamic programming, we will choose one path at each time, and that will lead to that yes, and that is the lucky choice, and by magic we will always get the lucky choice. I mean, we always get the lucky path. So, this is a fairy magic you can say. So, that is the lucky algorithm. So, lucky algorithm means we can make lucky guesses. So, every time we guess this, then we guess this, then we guess this, and this is not random. I mean, we are guessing and that is happen to be a lucky guess. So, that is basically a magic. So, can make lucky guesses always always write without trying all option. Like in dynamic programming problem, we are trying all option, but here we are just choosing one option, and that is the good guess, by guessing, that by magic say, without trying all options. So, this is what is referred as lucky algorithm. So, we are not going for all path, we are picking one path, and that is happen to be a lucky choice. That means, that will leads us to the answer yes. So, that means it is the lucky choice of that. Okay. So, this is called a non-deterministic model. So, this is, that is why it is called NP. So, non-deterministic polynomial. So, this is a polynomial time algorithm, but polynomial time, but non-deterministic way. It is not deterministic, I mean by magic, I mean we choose a lucky algorithm. So, lucky algorithm means we make the lucky guesses always without trying for all options. Okay. So, that is called non-deterministic model. So, let us write that. So, NP is non-deterministic polynomial time. So, what is non-deterministic? Non-deterministic model is algorithm makes guesses and then say yes or no. Okay. So, this model we cannot build in a real computer, but theoretically we can study this model. There is no real computer for which we can build this model, because we cannot, I mean what is the guarantee that we will be lucky always. So, this model is not realistic model, in the sense we cannot build this in a real computer, but theoretically it is okay, we can have a theoretical study on this. Okay. So, this means guesses are guaranteed. It is not say random guess, guesses guaranteed, to lead to yes outcome, if there is yes, lead to yes outcome if possible. So, that means, then suppose we start from here, there are few possibilities, then suppose we start here also few possibilities, suppose from here also few possibilities, suppose this leads to a yes, this is yes. Then, so every step, every path, every step we choose one path, not all possibilities. So, here also we have some move. So, this is our guess, and this guess is guaranteed in the sense we will always choose this path which will lead to us yes. If there is no yes, then there is no, I mean then the result will be no, but if there is a yes, if possible, then our guess is always correct. So, this is sort of magic. Okay. So, no realistic computer can guarantee that, but theoretically this is okay. Okay. So, this is basically the NP class. Now, this is another definition of NP class is, another way to view the NP class is, so it is a set of all decision problem with solution, decision problem with solution that can check in polynomial time. which solution can be checked in polynomial time. Okay. So, when the answer is yes, we can prove it. And we can check the proof in polynomial time. Okay. So, this is the another way to view the NP class. So, NP is non-deterministic polynomial time. Okay. So, one example of NP is Tetris. Tetris belongs to NP. So, we can have a non-deterministic algorithm. So, that means we can always guess and we can reach to a answer that whether we survive or not. So, this is basically our NP class. So, we can just write this up to this is our NP. Okay. And Tetris is belongs to, because we can very well have a non-deterministic algorithm, to I mean always we will choose by magic whether this can we can fit this way, always we can choose a option. I mean always we can have a guess algorithm which can lead to us whether we can survive or not. Okay. So, that way we can show Tetris is in NP. Okay. So, now we want to tell something about this NP and P. So, this is basically up to this it is NP. So, Tetris is belongs to NP. So, now we want to see now there are some conjecture like P is not equal to NP. So, NP is a harder problem, right? NP is polynomial time, it is a problem which can be solved by polynomial time, but with the help of a lucky algorithm. Okay. So, non-deterministic algorithm. So, that way it must be a this is sort of this is a conjecture, this is a open problem, $1 million problem. If you want to be famous, you can solve this problem. This is still a open problem. I mean our intuition is okay, this should not be equal set. So, people have tried whether equal, whether people have tried whether they are not equal, but there is no such proof so far P not equal to NP. But this is a conjecture that we have this must be the harder set, this must be the bigger set of problems than P. Okay. Another way is to say this P not equal to NP, if we believe this, that another way to say this, we cannot engineer the guess. So, that means we can believe on guess, but we cannot guarantee the guess, we cannot develop the guess. I mean, so this is cannot engineer the guess. Sorry, cannot engineer the luck. We can believe on luck, but we cannot guarantee on luck. So, that is the thing, we cannot engineer on luck. Okay. So, now our claim is if P not equal to NP, then the Tetris belongs to NP minus P. Okay. So, if P is not equal to N P, then the trace belongs to. So, this is the trace is the hardest problem in N P. Okay. And so, this is why it is called trace is N P hard as hard as every N P problem. So, it is the hardest problem among all N P problems. So, this trace is N P hard. So, it is the N P hard means it is the hardest problem among all N P problem. Hardest among all N P problem. Okay. So, this is called N P hard. So, that means from here all the problems are N P hard, and trace is here. So, trace belongs to this, and this is called N P complete problem. Okay. So, N P complete means which is basically intersection of N P hard and N P. So, which are the most hardest problem in N P. So, these are called N P complete, but N P hard is all the problems which are basically harder than given any N P problem, which are basically harder than all the N P problems are called N P hard. So, let us draw this picture here. Okay. So, how much time we have? Yeah, we are doing good. So, let us draw this picture here. So, this is the line of difficulty, computational difficulty. The line starts from here. So, here we have all easy problems, and here we have trace, and here we have exponential problem, and this is basically one problem is chessboard, n by n chessboard, and here we have R, which is basically set of all problem which can be solvable in finite number of times. And after R, all these problems are uncomputable. Like most of the decision problems are uncomputable. We have proved that in the last class. So, what we have seen? We have seen trace. So, this is basically N P, this is N P, and we have seen trace in N P, and we assume if we use the conjecture P not equal to N P, if P not equal to N P, then trace must be the one of them, which is in N P not in P, because we are not having any polynomial time algorithm for this decision problem. So, then if this is true, then trace must belongs to N P minus P. Otherwise, if we have P equal to N P, this is P, this is N P, if they are equal, then trace must sitting here. It is the hardest problem, because we have no polynomial time algorithm to solve this. So, that means, this is the hardest problem among the as hard as every. So, in fact, this is basically trace belongs to is N P hard. N P hard means set of all problem which are from here to here. So, they are basically N P hard. So, that means they are as harder than any NP problem. So, these are all problems which are basically harder than any NP problem, every NP problem. So, it is basically harder than as hard as every problem belongs to NP. And then we have seen that if this NP complete means NP intersection NP hard. This is NP complete. NP complete. So, this is the collection where these are NP problem, but these are as hard as all given NP. So, these are as much hard as any given NP. So, these are all NP complete problem, and Tetris is one of the example of NP complete problem. So, there are many NP complete problem. Tetris is one of these example. Okay. Now, similarly from here to here, these are exponentially hard, x hard, and we define exponential x complete. So, again this is a conjecture, NP is not equal to x, this is a conjecture. Okay. This is another conjecture, this is also an open problem. This is also an open problem. So, NP is not equal to xp, if NP is not equal to xp, so then we define this is hard, and then we define x complete is basically xp. So, then xp hard means x hard means this is the set of problem which is as hard as any given x problem. So, then that is called x hard, and this is the set, all problems are x hard from this set, and if we take the union intersection x hard, then this is called xp complete, and chase is one of the example of x complete. Okay. Chase is one of the example of x complete. So, this is the NP complete, NP hard. Now, we will talk about reduction. Okay. So, this is the reduction. This is the way we design the algorithm sometimes, most of the times, because reduction is basically we reduce one problem to another problem. Mostly we reduce many problems to the graph problems, and then we know the solution of this graph problem. So, that solution will give us the solution from this problem. So, this is basically reduction. This is a design technique. So, basically what is this? So, basically we have a problem A, we are reducing this problem to another problem B, for which we know the solution. We know the solution, we know how to solve it, we know how to solve this, how to solve it. Okay. Then in order to solve A, if we can reduce A to be another problem B, which will know the solution, which will know the program to solve it, then we know the program, we know the solution of A, because we have the solution of B. So, like for example, so this is some example of reduction we have done. So, like if we have a unweighted graph shortest path. So, this is the problem. We have a graph, unweighted graph, and we have to find the shortest path from one node to another node. So, what we do? We know the weighted graph shortest path. So, what we do? We reduce this, we convert this problem to the weighted graph problem. So, this is basically we can put the weight of each vertex is, weight of each edge is 1. So, this is basically we can convert this into weighted graph. That is it. So, this is one example. Another example could be longest path. So, we have given a directed graph, we need to find the longest path. So, we need to we know the shortest path. So, what we do? We just convert the weight into negative, then this will be the basically the shortest path problem, and then we have the solution for the shortest path problem. And then, so this is a design technique basically, this reduction, and we have used in many places there in order to. So, we basically convert this into a known problem for which we know the solution. Okay, so, now we just talk about how we can use this reduction to prove some something which is called NP completeness, like so say for example, three partition problem can be reduced to Tetris problem. So, what is the three partition problem? We have given a set, we have given a numbers, integers, n numbers. So, the question is whether we can group this into 3 groups such that sum of the each group is same. This is the 3 partition problem. We can partition this group into 3 groups, so that sum of each group is same, and this we know this is a hard problem. This is hard. So, this is NP complete problem. So, now when we use the reduction, A is reduced to B, now that means B is harder than A. Because otherwise, if we reduce this, if we can solve A, then we can solve B, if this reduction is in polynomial time. Okay. So, every NP complete problem, there are many NP complete problem. So, we can take any two problem and we can reduce one problem to another problem by polynomial time reduction. So, that this is one of the examples. So, that means, this is we know, this is a paper, this is we know is NP complete, this is a hard problem. So, this must be harder than this, because this we can transfer into polynomial time. Otherwise, if we can solve this easily, then we can solve this, because we have a polynomial time reduction from this to this. So, if we can solve this, then we have a solution for this, okay, because we have given this problem, we reduce to this problem. So, if we can solve this problem, then we got the solution of this problem, but we know this is a hard problem, this is an NP complete problem. So, that means this is so we can use the reduction to prove the NP hardness. So, this is also, so since this is NP hard problem, this is NP complete, this is also hard. Okay. This is also hard. So, there are some example of NP complete problems, and every NP complete problems we can reduce from one to another. So, these are some example of NP complete problems. So, one we have seen is called 3 partition. So, we have given a set whether we can partition into 3 groups such that sum of each group is same. So, we have given some numbers, sum of each group is same. Then the knapsack problem. So, knapsack problem is we have given some weight and we have given a target. So, we have to find a subset of this, so that the addition of this is the target. So, this is also called subset sum problem. Then the travelling salesman problem, travelling salesman problem. So, we have given a graph and we have some edge weight on the graph. So, a salesman has to travel, find the shortest path that visit all the vertices from the given graph. So, it is a decision problem again, whether we can have, so yes or no. So, most of the problem have a decision version. So, this knapsack problem also. So, instead of finding this subset, whether the answer is whether we can have a subset or not. So, that is the decision version of this problem. This is also called subset sum problem. Okay, then the longest common subsequence problem. Subsequence problem. We have seen this problem at the starting of the graph algorithm. So, for two subsequence, if we have given two string, two sequence, then this problem we have seen by dynamic programming. But if there are k string, if there are k sequence, then this problem is hard, if k is greater than 2. Then we have a problem called SAT problem. This is the first problem of NP complete problem. This is basically telling us, given a Boolean formula, is it ever true? So, suppose we have given say x and then not x. So, this is some sort of Boolean formula we have. Now, the question is it ever true? So, this type of problem, this is the first problem came into the literature, which is proved to be a NP complete problem. So, all the problems are NP complete problem. There are other many NP complete problems, but we can use the reduction to one problem to another problem in polynomial time. So, if we know one problem is hard, then another problem has to be hard. So, this is the NP completeness we can prove, because if we can solve this problem in polynomial time, then this problem is also will be solved in polynomial time, because this problem we reduce in polynomial time to this problem. Okay, so, this is the sort of computation complexity we discuss. So, thank you.